Hello everyone. Today we are going to learn calculus not only as a mathematical subject but as a practical toolkit for understanding real world motion, change and optimization. Many students think calculus is only about formulas, but in reality calculus helps us answer very important questions. For example, how fast is something moving right now? How does one changing quantity affect another? How can we estimate complicated values without doing heavy calculations? And how can we find the maximum or minimum point of a real physical system? In this lesson, we will focus on derivatives. A derivative tells us the rate of change. It converts geometry into motion. It converts a graph into prediction. It converts a physical situation into a mathematical model. So, when we see a curve, we are not only seeing a shape, we are seeing a system that changes. The tangent line tells us the instant direction of change. That is the central idea of this toolkit, using calculus to decode reality. In this toolkit, we have three main modules. The first module is tracking link motion, also called related rates. This is used when two or more physical variables change together. For example, when a balloon expands, its radius and volume change at the same time. If we know how fast the radius changes, we can calculate how fast the volume changes. The second module is approximating complexity, which uses differentials and linear approximation. Sometimes exact calculation is difficult or unnecessary. Calculus allows us to use a simple straight line approximation to estimate the answer very closely. The third module is optimization or extrema. This is used to find maximum and minimum values. For example, the highest point of a rocket, the lowest cost of production, the maximum area, or the best performance limit of a system. So today, we are not learning three separate topics. We are learning three ways derivatives are used in real situations: tracking, approximating, and optimizing. Let us begin with Module 1, Tracking Linked Motion. In real life, many quantities do not change alone. They are connected. When one changes, the other also changes. This is where related rates become useful. Look at the example of gears. The master gear represents time. As time moves forward, the radius and volume also change. If we have a sphere, its volume is given by the formula V equals 4 thirds pi r cubed. Here, volume depends on radius. Radius changes with time, so volume also changes with time. We are not only interested in the value of volume, we want to know how fast the volume is changing. This is why we differentiate both sides with respect to time. Using the chain rule, we get dv by dt equals 4 pi r squared times dr by dt. This equation means the rate of change of volume depends on the current radius and the rate at which the radius is changing. This is the key idea of related rates. We connect the variables first, then differentiate with respect to time. Now let us understand the general process for solving related rates problems. There are four steps. Step 1 is physical reality. First, draw the system. Do not start with numbers immediately. Identify what is changing and assign variables. For example, height, distance, radius, angle, or volume. Step 2 is the static link. Build an equation connecting the variables. This equation usually comes from geometry, such as the Pythagorean theorem, trigonometry, area, volume, or similar triangles. Step 3 is the engine. This is where calculus enters. Differentiate both sides with respect to time. Since the variables are changing with time, we use the chain rule. Step 4 is the snapshot. After differentiating, substitute the known values at that specific instant, then solve for the unknown rate. A very important warning is shown here. Do not plug in numbers too early. Keep the system in motion. First build the equation, then differentiate, and only after that substitute the values. This prevents many common mistakes in related rates problems. Now we apply the four-step process to a real example: automated rocket tracking. Imagine a camera is placed 5,000 feet away from a rocket launch pad. The rocket is moving upward. The camera must rotate so that it always points toward the rocket. The question is, how fast should the camera angle change? Let the height of the rocket be h and let the camera angle be theta. The horizontal distance is fixed at 5,000 feet. Step 1. Define the setup. The distance from the camera to the pad is 5,000 feet. The rocket height is h. The camera angle is theta. Step 2. Create the static link using trigonometry. In a right triangle, tangent theta equals opposite side over adjacent side. So tan theta equals h divided by 5,000. That means h equals 5,000 tan theta. Step 3. Differentiate with respect to time. The derivative of h is dh by dt. The derivative of 5000 tan theta is 5000 secant square theta times d theta by dt. So dh by dt equals 5000 secant square theta times d theta by dt. Step 4. Substitute the snapshot values. When the rocket height is 1000 feet, its upward velocity is 600 feet per second. So dh by dt equals 600 from tan theta equals 1000 over 5000. We get tan theta equals 1 over 5. Using this, we can calculate sec square theta. The final result shown is d theta by dt equals 3 over 26 radians per second. This means the camera must rotate at exactly that angular speed to keep tracking the rocket. This example shows how calculus connects physical motion with machine control. Now let us study a second case, water draining from a cone. The problem says water drains at negative 0.03 cubic feet per second. We need to find how fast the water height is dropping. At first, the volume formula for a cone looks difficult. V equals 1/3 pi r squared h. There are two variables, radius r and height h. But we only want the rate of height change dh by dt. So we need to remove r. This is where similar triangles help. From the cone's geometry, the ratio r to h is constant. According to the slide, r divided by h equals 1 divided by 2. Therefore, r equals h divided by 2. Now substitute this into the volume formula. V equals 1/3 pi times h over 2 square times h. That simplifies to V equals pi over 12 times h cubed. Now the volume depends only on height. Differentiate with respect to time. dv by dt equals pi over 4 times h squared times zh by dt. Now substitute the snapshot. When h equals zero point 0.5 feet and dv by dt equals negative 0.03, we solve for dh by dt. The result is approximately negative 0.153 feet per second. The negative sign is very important. It tells us that the water height is decreasing. This example teaches a powerful idea. Before differentiating, simplify the geometry. Now we move to module 2, approximating complexity. The main idea here is simple but powerful. Up close, every smooth curve looks like a straight line. This is the reason we can use tangent lines to approximate complicated functions. If we zoom in very close to a smooth curve, the curve becomes almost indistinguishable from its tangent line. The linear approximation formula is L of x equals f of a plus f prime of a times x minus a. Here a is the anchor point. It is a value we already know. F hour is the function value at that point. F prime hour is the slope at that point. Instead of calculating the complicated curve directly, we move along the tangent line near the point A. This is extremely useful in physics, engineering, computer science, and numerical calculation. It allows us to estimate values quickly and efficiently. Let us see how linear approximation works with a simple example. Calculating the square root of 9.1. The exact calculation requires a calculator. The exact value is about 3.0166. But using calculus, we can estimate it mentally. Let f of x equals square root of x. We want to estimate f of 9.1. We choose an anchor point close to 9.1 where the square root is easy. That point is 9 because square root of 9 is 3. Now we need the derivative. The derivative of square root of x is 1 over 2 square root of x. At x equals 9, the derivative becomes 1 over 6. So the linear approximation is L of x equals 3 plus 1 6 times x minus 9. Now substitute x equals 9.1. L of 9.1 equals 3 plus 1 6 times 0.1. That gives approximately 3.0167. The exact value is about 3.0166. So the error is extremely small. This example shows the power of linear approximation. We trade a tiny amount of accuracy for a very large reduction in calculation effort. Now let us understand differentials. The derivative form dy by dx equals f prime of x can be rewritten as dy equals f prime of x times dx. This notation is very useful. Here, px represents a small change in the input. It may also represent a measurement error. dy represents the estimated change in the output. The graph shows two changes. One is the actual curve change, usually written as delta y. The other is the linear estimated change, written as dy. For very small dx, dy is almost equal to delta y. This means differentials help us estimate how a small change or error in input affects the output. In real systems, measurements are never perfect. There is always some error. Differentials allow us to understand how that error travels through a formula. So differentials are not just notation, they are a practical tool for approximation and error analysis. Now we apply differentials to an error propagation example. Suppose an astronaut measures Earth's radius as 4,000 miles, but the measurement has an error margin of plus or minus 80 miles. We want to know how this error affects the calculated volume of Earth. The volume of a sphere is V equals 4 thirds pi r cubed. Using differentials, we write dV equals 4 pi r squared r. Here dar is the error in radius, dV is the propagated error in volume. The slide describes this as a shell around Earth. The solid core is the calculated volume. The glowing shell is the possible error caused by the radius measurement error. Now, instead of calculating two complete sphere volumes, we approximate the volume error using the derivative. The percentage error is shown as dV divided by V is approximately plus or minus 0.06. That means an 80-mile error in radius produces about a 6% error in the calculated volume. This is a powerful message. Small measurement errors can become large output errors when the formula contains powers such as r cubed. Now we move to module 3, optimization. Optimization means finding the best possible value. In calculus, this usually means finding maximum or minimum values. The slide shows a curve with different peaks and valleys. One peak is a local maximum. It is the highest point in its nearby region. Another point is the absolute maximum. It is the highest point in the entire domain. Similarly, the lowest point in the entire domain is the absolute minimum. In real life, optimization appears everywhere. A company may want to maximize profit. An engineer may want to minimize material. A scientist may want to find the maximum height of a rocket. A sports scientist may want to find the best angle or force for performance. The derivative helps us locate these points because at many maxima or minimum, the rate of change becomes zero or undefined. So, optimization is the science of finding important boundaries in a system. This slide gives us a diagnostic matrix for extrema. First, a local maximum occurs when the function value at C is greater than or equal to nearby values. In simple words, the curve reaches a peak in a small neighborhood. Second, a local minimum occurs when the function value at C is less than or equal to nearby values. The curve reaches a valley in a small neighborhood. Third, absolute extrema refer to the largest or smallest value in the entire domain. An absolute maximum is the highest value overall. An absolute minimum is the lowest value overall. One important note is that an absolute extremum can also be a local extremum. For example, the highest point in the whole graph may also be higher than all points near it. This classification helps us understand what kind of maximum or minimum we are dealing with. In problem solving, we should always ask, are we looking for a local best value or an absolute best value? Now the question is, where do extrema occur? This slide shows two possibilities. The first case is when the engine stops smoothly. This means the derivative equals zero. The tangent line is horizontal. Mathematically, f prime of c equals 0. This often happens at smooth peaks and valleys. The second case is when the engine brakes sharply. This means the derivative is undefined. The graph may have a sharp corner or cost and no single tangent line exists. A very important rule is shown at the bottom. If an interior local extremum exists, it must occur at a critical point, but we must be careful. Not all critical points are extrema. Some critical points may be flat but not maximum or minimum. So, in optimization, critical points are candidates. They are places we must check, not automatic answers. Now we discuss the extreme value theorem. This theorem tells us when absolute maximum and absolute minimum values are guaranteed to exist. If a function is continuous on a closed and bounded interval, then it must have both an absolute maximum and an absolute minimum. Closed means the endpoints are included. Bounded means the interval has a finite beginning and ending, such as from A to B. On the left side of the slide, the function is shown inside a closed interval. Because the interval has endpoints, the graph must have a ceiling and a floor. That means absolute maximum and minimum values exist. On the right side, the system is open from negative infinity to positive infinity. The function may have an absolute minimum at x equals 0, but it does not have an absolute maximum because the graph keeps going upward forever. This is why constraints are important. In real world optimization, we must define the domain clearly. Are we optimizing within a fixed range? Are there physical limits? Are endpoints included? Without constraints, a maximum or minimum may not exist. So, the extreme value theorem teaches us that optimization is not only about derivatives, it is also about the domain. Now, let us connect everything together. This final slide shows a unified physical situation. There is a radar tracking system, drones, motion paths, altitude, and optimization points. From this one situation, we can ask three types of questions. First, we can ask a relate rates question. How fast is the observer's radar angle changing right now? That uses the same idea as the rocket tracking example. We connect geometry with time and differentiate. Second, we can ask a differential approximation question. Where will the drone be in exactly 0.05 seconds? Here, we use the derivative to estimate small changes in position. Third, we can ask an optimization question. What is the absolute maximum altitude the drone will reach? For this, we look for critical points where the derivative becomes zero or undefined, and we also check the domain. So the message is very clear. One mathematical engine, three ways to decode physical reality. Derivatives help us track motion, approximate complex systems, and optimize performance. This is why calculus is not only theoretical, it is a language for describing the real world. Whether we are studying rockets, drones, water flow, measurement errors, or engineering systems, calculus gives us a structured way to understand change. To conclude, remember these three ideas. Related rates answer how fast is one variable changing because another variable is changing. Differentials answer how much does the output change when the input changes slightly. Optimization answers where is the maximum or minimum value. If you understand these three uses, you understand the practical power of derivatives. Thank you.